Again?
Switch again.
Okay, switch again. Okay.
Switch again. That time, which computer do I use? Maybe Taiwan. All right.
Okay, so we fixed the problem finally. So the talk is it's sort of, I got a little introduction from YQ in the morning, who spoke about some aspect of what I'm going to do here. But let me do the introduction to his talk. Now, I wouldn't have made it in the morning anyway, so. The aim of the talk is just to argue, and it's sort of mentioned by Dao Han, that the origin of neutrino mass obviously is a door to new physics. And I want to show you that hadron colliders can open the door. In a true sense, I want to argue that we have an actual self-contained complete theory for neutrino mass the way the standard model works for charged fermions. Now what it means to probe the mass, of course, it means the Higgs mechanism today, and the beauty of the standard model simplicity is that once you give Weinberg or Jim the mass of the lepton or the quark, they can predict the associated Higgs decay. And this is the only way. Unfortunately, we live in this funny vacuum that we live in, but you and I cannot know until we will hit a high temperature of phase transition. So you can see, of course, as you all know, the third generation works beautifully, W and Z mass. Slowly, the muon mass is being probed. And fortunately, there is a failure of the neutrino mass being zero in the standard model. So the task, the impeding task that we have to sort of go through is to find the analogous theory for neutrino, the way the standard model works. Now, if someone asks you, what is the crux? Why the standard model works? Why do we have this extraordinary simple prediction? Of course, it's a gauge theory, but equally important and not stressed enough, although we all know it, is the maximal parity violation, which reflects itself in the V minus A aspect of Fermi theory. It's a beautiful, by the way, essay by Weinberg 10 years ago. V minus A was the key, he says, to them to do it. Now why? Well, the obvious symmetry between the left and right-handed fermion forces you into a Higgs doublet. Weinberg simply had no choice when he wrote down the standard model Higgs particle. And remarkably enough, it works for all the particles of the standard model. And it works in such a way that everything is correlated. All you have to know, once again, the mass of the particle, and you will predict everything else. So for example, among the miracles, there is a natural flavor conservation, because when you diagonalize, obviously, the third point here. Anyway, when you diagonalize the mass, you diagonalize the Yukawa coupling. You all know this, okay? Also, this explains to us why the fermion masses live at the weak scale and are not very large. Now, to appreciate this, okay, everybody knows this, but I don't think this is appreciated enough. Do a little exercise, okay? If you're a student, do an exercise. If you teach in standard model, it's even more fun to do the exercise. Imagine that T.D. Lee and C.N. Yang had been wrong. And just look at the way the world would have been if parity remained preserved in weak interaction, just as in QED, okay? So I would have vector-like fermions. And now I have to do what Weinberg did in 1967. The first thing that I find out, fermions get a mass directly, obviously. So now there is a little miracle. Why in the world is the mass at the Electroweak scale and not much larger? Well, you say miracles happen. So I'll go on, says Weinberg. I have to introduce the Higgs. It has to be a triplet, obviously. Doublet and doublet gives me a singlet and a triplet. And I join, I have a Yukawa coupling. I go on. The vacuum expectation value of the triplet gives me up and down quark masses. Now, the natural flavor conservation tells me, look at the downforce. When the mass is diagonal, Yukawa should be diagonal, obviously, otherwise you will get too much flavorization in the current. Now, that immediately means that M is diagonal, and therefore M up and M down are diagonal simultaneously, and you have no flavor mixing. Also, with the triple, the Z mass is 0, you lose absolutely all the predictions. Weinberg would have never written this paper. Obviously, he would have given up because it just looked impossible to deal with. Okay. So it's a sort of funny thing that you have a left-right symmetric, which is the blessing. This is what was the crux. Weinberg says this is what you needed to end up with a standard model. Think of charge Fermion masses. And yet, at the same time, this is the source of the failure because the left-right symmetry tells us the neutrino is massless in the minimum model. In the vector-like world, however, the neutrino would have been massive. So that would have been a great thing. Okay, you would have a neutrino mass prediction. Okay, long before experiment. So it's a sort of kind of catch-22 situation. You want to have left-right symmetry for neutrino, and when you break it maxially for charged fermions, it's not surprising that it's going to work if you live in the left-right symmetric world and break the parity spontaneously. And it actually, I'm just telling you from the historical perspective of you and me thinking about this today, actually happened the other way around in the 70s. Some of us actually imagined that the world was left-right symmetric with simply having a right-handed scale. The U gauge was much heavier than much heavier than the light ones. And lo and behold, this predicted, obviously, as it would have been in the parity conserving way. Right-handed neutrino had to exist, and neutrino had to be massive. Here you have no way of having a massless neutrino. Neutrino is basically equivalent to the electron. Now, obviously the gauge group would have been extended. Briefly, I mentioned the left-right symmetric world. The generator U1 becomes B minus L. You need a new Higgs sector, and you need a Weinberg-Salam doublet that has to live in the representation of the group. Obviously, there are two SC2 groups, so it's a bi-doublet. The new Higgses, there is, of course, a new Higgs sector. In this particular modern version of the theory, are the SC2L left and right triplets, which carry B minus L charge. And parity is broken spontaneously. You show that by the right-handed guy, definition of right-handed getting a vacuum exponential, and explaining why everything else is heavy. All the new particles, including the right-handed neutrino, go to the large scale. The important thing here, when you write down the Yukawa couplings, the standard model Yukawa couplings with a bi-doublet, okay, generalized. We'll see in the moment the restriction that come out because of the left-right symmetry. There are new Yukawa couplings of the new scalars. The triplets, of course, for the Yukawa couplings, you have a Dirac master, which naively you would have expected that the mass of the neutrino was equal to the electron mass. And this was the curse in the beginning. You know, people were telling us, I was being told I was wasting my time, neutrino would be very heavy. The answer comes in the symmetry breaking. The right-handed neutrino gets a heavy, becomes a heavy Majorana ultra lepton, picks up the mass through the same vector interpretation value that gives the mass to the right-handed gauge boson. Actually, it's neither right-handed nor neutrino, because it always has a left-handed counterpart. I find here the anti-particle. The left-right symmetry, what it does to us, remember, under the left and right SC2 groups, the fermions transform, of course, the doublet. The bi-doublet is bi-doublet, transforming as left and right. So if you look now and cause the left-right symmetry, which you have to do that in the program of attributing the parity breaking to spontaneously broken original symmetry. In the case of parity, it's easy to see the transformation property of phi, left goes to right, Yukawa couplings would be Hermitian. And the left and right triplets will have the same coupling. The charge conjugation, which is an equivalent left-right symmetry, the only thing in the charge conjugation that you go to the complex conjugate, it's easy to see the complex conjugation here will give you the transpose, and Yukawa couplings will be symmetric. Okay? It's just a minor technical point, but it has a profound role, as I will show you in a moment. So just try to remember it when I go on. Okay, a few technical details. And the answer, of course, is the seesaw mechanism, which is often sort of a celebrated explanation of why neutrino is massless. To me, a little troubling, because we often say that neutrino is massless in the seesaw because this guy is heavy. But unless I show you how heavy it is, I show you how to find it, to find the mechanism of probing it. This was, of course, more semantics than actually explanation, because really, light neutrino tells me that then it's heavy, not the other way around. Okay? So the point here, which is fundamental in the theory, the guy gets the mass at the light scale, so at least that is the tribute to the left-right symmetry. And of course, I have to know something about M. Dirac in order to be able to claim that I can probe neutrino mass. So the physical picture, of course, is you understand why Gleshow, Weinberg, and company claimed that neutrino is massless, because for them WR was infinitely heavy, and in the limit of maximum parity violation, neutrino mass was 0. There is actually, I cheated a little bit, there is an induced, okay, typically the well-known mechanism of isospin, hierarchy of the isospin breaking, okay, the triplet gets a tiny web. This is not a Higgs. There is no Higgs mechanism, okay. This guy only has a tadpole, and its vacuum expectation value is controlled by the weak and reduced scale. This is called type 2 seesaw. I'm not a lover of these words, okay, because obviously once you have the mechanism that attributes the large scale to the small neutrino mass by doing variations, you have other sources. You see, for example, the question whether you should use seesaw 1 and 2 in a well-defined theory gets answered. Both are present, and both are controllable and predictable. I will ignore this for simplicity in the talk. There is no loss of generality in what I want to show you in the next few slides. So when I want to talk about the origin of neutrino mass, what is your and my task? You see, the crucial thing in the seesaw mechanism was the ratio of the, obviously, Dirac mass term to the mass of the heavy guy, right? The mixing angle between light and heavy neutrino is called controlled by obviously ambiguities. If I know this mixing angle, I can predict basically everything. For example, a particularly interesting process is the right-handed neutrino decaying into a charged lepton and W. There are other processes because of Higgses, okay? So I have a theory of mass if I can predict M. Dirac or theta. If I want to do what Weinberg did for charged fermions, you see, Weinberg tells you, give me the mass of the fermion, I'll compute the physical process that tells you how to probe the origin of mass. So you have to give me the mass of the, say, right-handed neutrino, and then if I would claim success, I have to do the thing that is done for charged fermion. I will have to compute M. Dirac, the associated Yukawa coupling. For this, I know the mass of the both light and heavy neutrino, right? This is the main difference between neutrinos in the seesaw picture and charged fermions, which sort of nicely tells you why they're different, being Majorana states. Whereas Dirac particle is one and the same particle, right? Electron and positron have the same mass. Left and right electron have the same mass. I need both mu and Mn. But the principle is the same. And mu, of course, we have been measuring. We are about slowly but surely disentangling. Mn would have to come from new physics and colliders. Now you can say, who cares about left-right symmetry? Now that you told me that there is this seesaw mechanism, why don't I just forget about it and just simply look at the seesaw by itself? I add a right-handed neutrino to the standard model. This is now called the seesaw mechanism. I forget everything about the rest of the picture. Now again, if I want to have a handle of what is going on. I need, let me emphasize once again, I need to know this mixing angle. I need to be able to have a handle on Andira. Because otherwise this would be worse. Its passion, of course, is very heavy, and I don't produce it already. And there is a trouble. It's easy to see when you look at this matrix because of the transpose that you can't solve for Andira. There is an arbitrary complex orthogonal matrix that simply cancels out. So this would fail. I could not disentangle seesaw. I can't make predictions for Andira, okay? Because this has a huge ambiguity. By the way, large, complex orthogonal matrices don't even have small elements. The element of a orthogonal matrix, when it's complex, can be as large as you wish. Unlike the real matrix, which can sign in both sides. Now, this can be used, and in all fairness, one can say I can limit the parameter space. I can assume then that data is very large. Not really a seesaw picture, I would call it, where it says the seesaw is beautiful because data is very small. You say, I will make data very large because I will choose, very, very large. Huge. As huge as I need it to make Andira large, so that I can produce the right-handed neutrino. Not really what we are. So I want to go back to the theory itself, the one that gave me the right-handed neutrino and that has the handle I will show you on what I'm after, or having the true self-contained theory that makes structural predictions. Of course, you can parameterize your ignorance of neutrino masses the way Weinberg does, when some years later he also changes his mind about neutrino masses and writes the effective operator that Ao flashed also quickly. If you have only the standard model states, of course, the only way is the 5-dimensional Weinberg operator. They became very famous. I'm not sure why. I think because it's due to Weinberg. All that it tells you, by the way, if you look at Yukawa couplings, they get extraordinarily small, and there will be no way of measuring these Yukawa couplings of the peaks. They are controlled by neutrino mass over NW. Moreover, what Weinberg operator tells you, it's being used as a sort of effective theory of Fermi. But the Fermi theory was a theory of many different physical processes that I could describe effectively at low energy. Here, what Weinberg says, there is absolutely no physics, he says, because all the physical processes, and he's giving talks still to this day. I had a strong disagreement last year in past course, which led to a long correspondence. And so that we argued it in Austin in the spring. He would tell you they don't study the origin of neutrino mass because all the new physics will be controlled through his operators by small neutrino mass. I'll actually argue that this is the wrong operator to look at. I'll show you in a few seconds. So anyway, what does emerge from all these pictures, even if you don't like left symmetry? All that I ask you that you believe in Majorana would tell you that then you have a Lepton number violation, as all of you know, which is a textbook classical example of neutrino double beta decay at low energies. Actually, first study series by Fury. And the work that I've done with Wai-Kyung, who is here, the analog hadron colliders, such as at the LHC, that you will see that in this left-right symmetric theory, there is a profound, deep, precise connection between these two physical processes. Neutrino double beta decay is often claimed to be the probe of Majorana mass on neutrino because of the obvious fact that once you have a Majorana mass on neutrino, you get a non-vanishing neutrino double beta decay. However, you can't argue the other way around because, for example, in any theory beyond the standard model, in particular this one, remember, there is no Majorana neutrino without ultraviolet completion. Therefore, for example, in this theory, there will be a new contribution. If there is left, there is right, to the right-handed neutrino. And they are competitive when these particles are in the TV region, which is kind of nice. So, an important comment when you look at the dependence on the neutrino double beta decay or neutrino mass. For example, if you and I establish that the hierarchy is normal, this wouldn't be proved in this generation of experiments. That is more or less here. So normal hierarchy established from some other physics would actually tell you that new physics does a neutrino double beta decay. Or for example, imagine you could measure the polarization of electrons coming out. It would tell you, if it comes out right-handed, that new physics is behind it. You could try to disentangle it with different isotopes. But a priori, by the way, in a left-right symmetric theory, this is just an illustration for some values of the masses. This is not, I need to know these masses are right-handed. You will have the opposite effect. And when you sum them, you boost the neutrino double beta decay. Now here's an important argument. We summarize it. I don't care what the new physics is. You may like supersymmetric Thunder model, you may have a model of your own. The point is that the fact that the neutrino double beta decay is a 6 Fermion operator of dimension 9 tells you this is the same limit, the same logic that gives you the limit of neutrino mass, tells you that if the new physics is doing the job, it has to lie at very low edges. Custom fit for, say, LHC, simply from the fact that the measured lifetime is bigger than to the 25 years. Now notice an interesting difference. The analog for barrier number violation, effective operator, tells you that non-observation of proton decay, the scale has to be 10 to the 50 GeV. And this I find very strange that it's not stressed enough. That there is a genuine reason for having physics that the TeV energy has nothing to do with naturalness. If you observe neutrino double beta decay, and the new physics does it, it has to be at this energy. In the 80s, we were hit with a crisis. There was some struggle around 83 that the WR had to be large, and there was no reason to really work on that, okay? The last paper that I've written was in 1983. I think the most important that I've written on this with YQ, who is here. And he talked briefly this morning. What we argued that when you produce the right-handed neutrinos through the brilliance through the production of WI, just as the production of W, because of the guy being Majorana, half of the time it would, well, first because of being Majorana, it would give you direct lepton number violation, so you could see better colliders. You would have the same sign, dileptons and the jazz. And of course, once it's Majorana, by Majorana nature, it tells you that half of the time it will decay into a lepton, half of the time into an antilepton. And I think this is sort of worth stressing as a major thing. This is a unique way of probing the Majorana nature of a fermion. Okay, not an indirect thing. This guy is a Majorana if you see half of the time decaying into same and opposite signs. This, I'm saying, once it's produced on shell. I talked briefly this morning about what happens when it's off shell. I will skip that. How much time do I have? I didn't pay attention. Did you? 7 minutes. I think I could leave this for the question. Okay, this is all tied. The theory is really tied to lepton flare violation. But let me not focus on it now. Ask me please if you're interested. We'll come back to it. Maybe actually I could. Just a few words. It is often claimed that there is a sort of history, if you have new physics, why the lepton flare violation is not much larger than what it is. And this is not a good argument because it always depends on the parameter space of the theory. Remember that the reason that the standard model works is simply because charm is light. There is no magical reasons beside that. If charm had a mass of the order of MW, you would have had a huge violation of strangeness. Say. So as you can see here, the amount of the particular intrinsic process is the mu going to electrons, so the three-level exchange of the doubly charged states in the triplet. So all that you need is that these guys being heavier than the right-handed neutrino. Not surprising, the right-handed neutrinos are controlled by the Ogawa couplings, okay, so this wouldn't be a problem. Or, and they could be somewhat degenerate. Okay, there is nothing mysterious about that. Although you cannot make predictions, of course, you can never know in a theory beyond the standard model what is going on unless you hit the scale. There is a nice correlation, which is worth emphasizing, between mu going to a gamma and the muon conversion. Simply because the dominant, due to its charge, the dominant contribution is from these doubly charged particles. And it's very easy to see that they are more or less of the same size. This has been decided in the PhD thesis of Lepton, my ex-student, with whom I have been working in recent years, but what I will touch in a minute. So I think you may have mentioned in the morning, okay, there is a now dedicated search by CMS and Atlas that has established the limit in the process that I showed a few minutes ago, roughly around 5 TeV, but it depends on what you assume about right-handed masses. There is a hard limit just from digests, which of course doesn't care about any other decay, which is 4 TeV. A side comment for those of you that are interested, recently with Lepton, we solved the long-standing problem of 40 years of a kind of holy grail study, which was lacking, and it has a profound consequences, the analytical determination of the right-handed quark mixing angle. Although the parity is maximally broken, the memory stays in the Higgs picture. And it's interesting, Glaf, there is a conspiracy because of the same small mixing angles of the standard model. What you find out that the right-handed and the left-handed mixing angles are basically the same. They're suppressed by the small mixing angles of the standard model, which justifies all the limits that the LHC automatically assumes. They never do really complete study. They assume that these mixing angles are the same. They actually are. So you can trust the numbers that they give you. Okay, now it's sort of I'm about to finish, but this is maybe the most important slide, remember what I said, if the left-right symmetry is charge conjugation, your Kawa couplings got to be symmetric. If they are symmetric, the Dirac mass terms are symmetric. So the seesaw formula, there is a sign here that I don't care about. Okay? The seesaw formula gets simplified, and it's obviously divided by a man on both sides, and you get a quadratic equation for MD. It is uniquely determined. If you wish, that ugly matrix that troubles you in the seesaw picture, that prevents you from making prediction, gets fixed now. But who cares? That was just a way of talking about the ambiguity. So for example, imagine this is just for illustration that the right-handed and left-handed leptonic mixing are related. You will have a very simple formula for MD. And as I told you, I can compute immediately the decay rate, for example, a heavy neutral lepton decaying into a W and charged lepton. And as I said before, once again, the same way that you need the mass of the charge fermion in the standard model to probe the Higgs mechanism, all you need here are the masses of the light and heavy, iron and neutrino. So this is a fundamental point that I want to make. The theory is self-contained. Okay, I have made no assumptions whatsoever beyond the structure I started with. And obviously, what we need is the measure of the masses and mixings that we are probing in the low energy and the high energy. The golden channel is the one that I showed you before. There are other channels, of course, because of the scalars that are present, doubly charged scalars and so on. This is all correlated. We recently wrote a paper at the end of the last year giving the table of all these interconnected processes, okay? Most of it happened, by the way, by our surprise. We didn't expect this to work, okay? This we could have seen 40 years ago. But sort of like the student who studies at the last moment before the exam is the LHC that forces us to look into the structure. When the left-right symmetry parity, the situation gets far more complicated because the Dirac matrix is Hermitian, so you don't have this simple M here, you get M star. And it's a mess. It's not trivial mathematical challenge. It took us time to solve. I'm not going to argue with that. Ask me if you're interested into it, okay? I'll just tell you what happens. For example, in the case, we solved the problem only recently. Again, as an illustration in the possibles, right-handed mixing angle. Again, the Dirac-Mass matrix, you can see it's manifestly ordered seesaw. There is no ambiguity whatsoever. If AR is not equal to VL, the formula gets a little more complicated, but I will know it. Here is the latest delegated study that talks about the LHC search. They somehow conclude that you could see WR claim the discovery around 6 TeV, see the signal even at larger values. People already think about 100 TeV reach, okay, and then you'll have to wait. I think I can summarize at this point. I tried to convince you that what I wanted you to take from this talk is that the theory actually is completely self-contained. What is, I mentioned it already a few times, what is interesting that you have a link, which is one-to-one link between the LHC and low energy experiment. Neutrino's double beta, Lepton flavor violation. But it's amusing that all these experiments are happening at the same time scale. We live in an interesting era. They're probing the same physical scale, and we are talking about the same time scale. And the crucial experiment, of course, is Neutrino's double beta decay. That being observed would be an important argument in favor of a lower scale of WR. Thank you.
Questions?
So you showed some loop processes for the Lepton flavor violation. And I guess the same similar diagram will also contribute to mu G minus 2.
Yeah,
Involving double check. Have you considered that?
This is an important question. No, I didn't myself consider that. There is a, it's a very, I'm glad you asked, actually. I was thinking whether I should mention it, but it's even nicer when it's a question. Of course, the G minus 2 is flavor conserving part, right? So you can't, before you know the mixing angles, you can't establish really one-to-one ratio. But yes, it would contribute, and it could, the WR itself tends to be a little too heavy to G minus 2. When we put a number, the WR contribution. The delta, the charge, the doubly charged one, as you have noticed, yes. The doubly charged one could be, you know, if the G minus 2 anomaly were to persist, it could fit the, because the limit on the doubly charged guys, which I should have mentioned, is far lower than the limit of WR. You produce them pairwise. It's about 400 GeV or so. And it's nice that both could live together because Lepton flavor violation, which is rather sensitive, more than G minus 2, of course, is controlled by mixing angle.
Goran, I want to understand more about this one-word operator you mentioned. You seem to downplay this one-word operator. And you use the dimension 9 operator to describe this neutrino operator. Yeah. But dimension 5 will contribute. Why dimension 9?
Well, dimension 5 just contributes. Dimension 5 tells you the following. Dimension 5, what Weinberg writes, tells you that neutrino is a Majorana particle. That's all. All the new physics disappears. So it's actually not an operator of physics. It's an operator for a mass, for a parameter of the theory. What I want to argue, and I think this is crucial, okay, at least when I gave a talk in Austin, Weinberg, for example, agreed and insisted strongly that we looked wrongly at Weinberg's operator. The operator to look at, you see, when Weinberg, by the way, in the same beautiful paper, this is Weinberg, 1979, if you haven't read, you know, this is an extraordinary thing. Weinberg, by looking at this operator, dimension 6 operator for proton decay, can make a number of beautiful predictions. You know, interesting things about kaons in the neutron proton decay, about isospin and so on, because this is a genuinely operator that describes new physics, not just as some mass parameter. The analog operator is this one. This is the thing that we are probing. The holy grail search for proton decay for us is Neutrino's double beta decay. And actually people are now studying this seriously. Gasser at Los Alamos and other people are now tabulating these operators, because this now you should correlate just the way you would do here. You could make some independent prediction by studying the effective operators. And this one, I like the, you see, Weinberg used to argue continuously that because of the cutoff in his operator being 10 to the 14 GeV, forget about looking for the Neutrino mass. But this is the element operator, the cutoff is very low. This to me is by far the best argument that there could be new physics at the LHC or the next collider. This cannot fail. If you observe neutrino double beta decay and you have a normal hierarchy, it's coming from here. So you better be ready. So if you have another favorite model, just make sure that you study this contribution, okay, when it's a genuine. I think the same thing will happen in MSSM. It's just hard to make predictions, okay, because of many parameters. It's a model-dependent statement, and I think this is somewhat overlooked.
I have one question. Yeah, I missed one point. So you assume the left-right symmetry, but somehow you need additional Majorana neutrino. So in one part of this model.
Well, you know, there is a, that's an important question. What is it you are saying that breaks the symmetry between the left and right? Remember that I had to break the symmetry spontaneously anyway. So when I break the symmetry, when the right-handed field gets a vacuum expectation value, this is at the first stage of symmetry breaking, when you forget the Electroweak symmetry breaking. This vacuum expectation value gives the mass to the right-handed neutrino. So this is what is happening. So the one and the same Higgs mechanism that makes WR and you ZR very heavy. So here it is happening. Of course, you may complain. You know, whatever theory you write depends on what Higgs you have used. In this minimal picture, this is what happened. The same way that you look at the standard model, everything depends on the Higgs you use. Fortunately, the standard model works for this extraordinary, minimal, simple scenario. That's why, I want to say this is structural. There is only the first symmetry.
So let's thank the speaker again. Yeah.
Thank you.
The next speaker is